Hello aspirants, welcome to Magic World of Physics. In this video, we're going to discuss about some questions from atomic and molecular physics which is asked in various exams like GATE, Barc, Justifer. Hope this video will be helpful for your coming Barc exam 2026. Without any further delay, let's get started. The first question is, which of the following is the spectroscopic ground state 2s plus 1 Lj for Mn3 plus ions of the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d4 predicted by Hund's rule? The electronic configuration for Mn3 plus ions is given as 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, and there are 4 unpaired electrons in the d orbit. So here the Ml values are -2, -1, 0 and 1, and for each unpaired electron the S is half, so that S is equal to half plus half plus half plus half, and this is equal to 2, and L is equal to summation over Ml, and this is equal to -2, -1 plus 0 plus 1, and this is equal to 2, and we know that J is equal to L minus S to L plus S, and this is equal to 0, 1, 2, 3, 4, and here the orbit is less than half filled. That means the J value of the ground state is J is equal to J minimum. That means it is L minus S, and this is equal to 0. The spectral term for the ground state can be written in the form 2s plus 1 Lj. Here L means it is the d orbit, then 2s plus 1, that means 2 into 2 plus 1, that is equal to 5, and J is equal to 0, that is 5d 0. So the answer is option A. Next question is, the Bohr model gives a value for the ionization potential of Li2 plus ions as dash. So here by the Bohr model, the energy of the hydrogen-like atom is En is equal to msh square e raised to 4 divided by 32 pi square epsilon 0 square h cut square n square. And for ground state energy, that means for the ground state level n is equal to 1. That means here E1 is equal to minus Z square into 13.6 into EV. For lithium, Z is equal to 3. Therefore, E1 is equal to minus 3 square into 13.6 EV, and this is equal to minus 122.4 electron volt. Therefore, the value of the ionization energy of Li2 plus is 122.4 electron volt. So the answer is option D. The next question is, if the wavelength of the first line of the Balmer series in the hydrogen spectrum is lambda, then the wavelength of the first line of the Lehman series is dash. For the first line of Balmer series, Ni is equal to 2 and Nf is equal to 3. Therefore, the equation can be written as 1 by lambda is equal to R into 1 by 2 square minus 1 by 3 square. Therefore, 1 by lambda is equal to R into 1 by 4 minus 1 by 9, and this is equal to 5R by 36. Therefore, R is equal to, that means the Rydberg's constant is equal to 36 divided by 5 lambda. This is equation number 1. And for the first line of Lehman series, Ni is equal to 1 and Nf is equal to 2. Therefore, 1 by lambda is equal to R into 1 by 1 square minus 1 by 2 square, and this is equal to R into 1 minus 1 by 4, that is, it is equal to 3R by 4. Substituting the value of R from equation number 1, we can write it as this is equal to 3 by 4 into 36 by 5 lambda, and this is equal to 27 by 5 lambda. Therefore, lambda Lehman is equal to 5 lambda by 27. So the answer is option B. The next question is, the degeneracy of an excited state of the nitrogen atom have electronic configuration 1s2, 2s2, 2p2, 3d1s. So here to find the degeneracy, we need to consider the subshells having the unpaired number of electrons. Here the subshells are 2p2 and 3d1. So we need to take the degeneracy for 2p2 and 3d1. Let the degeneracy for 2p2 be d1 and for 3d1 it is d2. Then the total degeneracy is d is equal to d1 into d2. And the general equation for the degeneracy is 4l plus 2 the whole factorial divided by 4l plus 2 minus 1 the whole factorial into n factorial. Therefore, here for the D1, that means D1 is a degeneracy for 2p2, So for 2p2, L is equal to 1 and the number of electrons present is 2. That means N is equal to 2. L is equal to 1 and N is equal to 2. Therefore, D1 is equal to, substituting all these value in the equation, we can write this is equal to 4 into 1 plus 2 the whole factorial divided by 4 into 1 plus 2 minus 2 the whole factorial into 2 factorial, and this is equal to 6 factorial divided by 4 factorial into 2 factorial, and this is equal to 6 into 5 by 2, and this is equal to 50. Similarly, we can do this calculation for D2. D2 is the degeneracy for 3D1. For 3D1, L is equal to 2 and N is equal to, that means the number of electrons is 1. Therefore, D2 is equal to 4 into 2 plus 2 the whole factorial divided by 4 into 2 plus 2 minus 1 the whole factorial into 1 factorial. And this is equal to 10 factorial divided by 9 factorial, and this is equal to 10. Therefore, D is equal to D1 into D2, and this is equal to 15 into 10, and this is equal to 150. So the answer is option D. Next question is, which of the following represent the 3p radial wave function of the hydrogen atom? The radial wave function RNL of R of the hydrogen atom should satisfy some condition. That means it should vary as R raised to T for small r, and it decreases exponentially at large value of R, and it has n minus L minus 1 radial knots. So here the state given is 3p. So for the 3p state, n is equal to 3, L is equal to 1. Therefore, the Rn plus will vary as R for small value of R, and it decreases exponentially for large value of R, and it has 1 node. So only option B satisfies all these conditions. So the answer is option B. The next question is, the intrinsic or permanent electric dipole in the ground state of hydrogen atom is dash. The electric dipole moment of a system is the product of the charge and the separation between the positive and the negative charge centers. A permanent or an intrinsic electric dipole moment can only exist in a system where the centers of positive and negative charges do not coincide. Here in this hydrogen atom, the electron's probability crowd is spherical in shape. It is spherically symmetric around the proton, that means around the nucleus, and due to this spherical symmetry, the center of the negative charge distribution coincide with the center of the positive charge. As they coincide, the intrinsic or the permanent electric dipole moment of the ground state of the hydrogen atom is 0. So here the answer is 0. Next question is, which of the following is a dimensionless constant? By Coulomb's law, F is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. Rearranging this, we get epsilon 0 is equal to Q1 Q2 divided by 4 pi F into R square. Therefore, the dimension of permittivity is m raised to minus 1, L raised to minus 3, T raised to 4, I raised to 2, or m raised to minus 1, L raised to minus 3, T raised to 4, A square. A means the ampere. And to find the dimension of permeability, we know that the force between two parallel current carrying wire is F by L is equal to mu 0 I1 I2 divided by 2 pi d. Rearranging this, we get mu 0 is equal to 2 pi df divided by L I1 I2. Therefore, the dimension are ml t raised to minus 2 I raised to minus 2 or ml t raised to minus 2 a raised to minus 2. So permeability also have the dimension. Then for Bohr magneton, we know mu b is equal to EH cut divided by 2me. Therefore dimension is L square t raised to minus 1 I or L square t raised to minus 1 a. So it also has the dimension. Next option is the fine structure constant. It is a physical constant representing the strength of electromagnetic interaction between elementary charged particles, and it is defined as alpha is equal to E square divided by 4 pi epsilon 0 h cut c. When the dimensions of all the constant particles are combined, then they cancel out, making the fine structure constant a dimensionless quantity with a value of approximately 1 by 137. So it is a dimensionless quantity. So the answer is fine structure constant. Different spectral lines of the Balmer series falling one at a time on the Young's double slit apparatus. The separation between the slit is d and the screen is placed at a constant distance from the slit. What factor should d be multiplied by to maintain a constant fringe width for the various lines as n takes different allowed values? For Young's double slit apparatus, the fringe width beta is equal to lambda d by d. Then for Balmer series, nf is equal to 2. And we know that 1 by lambda is equal to r into 1 by nf square minus 1 by n square. Here nf is equal to 2. Therefore 1 by lambda is equal to r into 1 by 2 square minus 1 by n square. And the simplest 1 by lambda is equal to r into 1 by 4 minus 1 by n square. Therefore 1 by lambda is equal to r into n square minus 4 divided by 4n square. Therefore lambda is equal to 4n square divided by r into n square minus 4. So here, substituting the value of lambda in the beta, we can write beta is equal to 4n square d divided by rd into n square minus 4. For beta to be constant, the ratio lambda by d to be constant. That means lambda by d is equal to a constant. That means lambda is proportional to d. That means d is proportional to 4n square by n square minus 4. So, to maintain the constant fringe width, d should be multiplied by a factor proportional to 4n square divided by n square minus 4. So, here the answer is option C. The next question is, in a Stern-Gerlach experiment, the atomic beam whose angular momentum state is to be determined must travel through. In Stern-Gerlach experiment, the transverse deflection suffered by an atom, that is d, is proportional to dou Bz by dou Z. If the field is homogeneous, then dou Bz by dou Z is equal to 0. Therefore, d is equal to 0. And if the field is inhomogeneous, then dou Bz by dou Z not equal to 0. And it will produce a finite transverse separation between the up and the down spin atom. So, the answer is option C. Next question is, under the LS coupling scheme, the possible spectral terms 2s plus 1lj for the electronic configuration 2s 3s are. So here for 2s, s1 is equal to half and l1 is equal to 0. For 3s, s2 is equal to half and l2 is equal to 0. Therefore, s is equal to s1 minus s2 etc. up to s1 plus s2, and this is equal to 0 and 1. Then L is equal to L1 minus L2 to L1 plus L2, and this is equal to 0. Then for S is equal to 0, L is equal to 0, J is equal to 0, and here 2s plus 1 is equal to 1. Therefore, the spectral term is 1 as 0. Then for S is equal to 1, L equal to 0, J equal to 1, and here 2s plus 1 is equal to 2 into 1 plus 1, and this is equal to 3. Therefore, the spectral term is 3s1. So here the answer is option C. The next question is, the Landé G factor for 3p1 level of an atom is. For 3p1, L is equal to 1, J equal to 1, 2s plus 1 is equal to 3. So here S is equal to 1. Therefore, Landé G factor, that is G is equal to 1 plus J into J plus 1 minus L into L plus 1 plus S into S plus 1 divided by 2J into J plus 1, and this is equal to 1 plus 2 minus 2 plus 2 divided by 4, and this is equal to 1 plus half, and this is equal to 3 by 2. So the answer is option B. Next question is, in a Stern-Gerlach experiment, the magnetic field is in the plus Z direction. A particle comes out of this experiment as in plus Z state. Which of the following statement is true? Here it is given that the magnetic field is in the plus Z direction and the particle comes out in the plus Z state. Therefore, a particle is in the eigenstate of the Z component of the spin Sz. It has a definite measured value for Sz. However, the x and y components of the spin, that means the Sx and the Sy, are complementary observables to Sz. Therefore, due to the uncertainty principle, these values cannot be measured simultaneously. So, the option A, C, D become incorrect. Then the square of the total spin angular momentum operator, that means S square, commutes with all the components Sx, Sy and Sz. This means that a particle can simultaneously have a definite value for its total spin squared and one component of its spin. So if you take an example of a spin half particle, S square value is equal to 3 by 4 h cut square. So regardless of the direction of the measurement, it always have a value for S square. So the answer is option B. Next question is, the spectral term for the atom with 70% filled subshell and only S is equal to 3 by 2 is dash. We know that the spectral term can be written as 2s plus 1 Lj. So here it is given that S is equal to 3 by 2. Therefore 2s plus 1 is equal to 2 into 3 by 2 plus 1, and this is equal to 4. So option A and C is wrong. Then here it is also mentioned that the subshell is 70% filled. For a D subshell, if it is 70% filled, it means it can accommodate 10 electrons and it contains 7 electrons. And for an F subshell, it can accommodate 14 electrons and here it contains 10 electrons. Then we need to check the other option. In option B, it is given that 4F 9 by 2. The letter F corresponds to L equal to 3. Then the J value is 3 plus 3 by 2. That is equal to 9 by 2. And this matches the option. Then for option D, it is given that 4P 1 by 2. The letter P denotes L is equal to 1. Therefore J is equal to 1 plus 3 by 2, and this is equal to 5 by 2. Here the value of J doesn't matches with the value given in the option. Here the value given as half. So the option that matches is option B. So the answer is option B. The next question is, the spin orbit coupling constant for the upper state of the sodium atom which emits D lines of the wave number 16956.2 and 16973.4 centimeter inverse is dash. For sodium, the ground state is 2s and the excited state is 2p. The spin orbit interaction energy is E is equal to A by 2 into J into J plus 1 minus L into L plus 1 minus S into S plus 1. Here J is equal to L plus S and A is the coupling constant here. So for the ground state configuration, that is 2s, L equal to 0, S is equal to half. Therefore J is equal to L plus S and this is equal to half. So the ground state energy level is 2s half. There is only one J value, therefore there is no splitting. Then the excited state term is 2p. Here L is equal to 1, S is equal to half, then J is equal to L plus or minus half, and this is equal to 3 by 2 and 1 by 2. So the level will split into 2, that is 2p 1 by 2 and 2p 3 by 2. Let A dash be the coupling constant for 2p level. So the energy for 2p 1 by 2 is equal to A dash by 2 into 1 by 2 into 1 by 2 plus 1 minus 1 into 1 plus 1 minus 1 by 2 into 1 by 2 plus 1, and this is equal to minus A dash. And the energy for 2p 3 by 2 is A dash by 2 into 3 by 2 into 3 by 2 plus 1 minus 1 into 1 plus 1 minus half into half plus 1, and this is equal to A dash by 2. Therefore, the energy change delta E is equal to E of 2p 3 by 2 minus E of 2p 1 by 2, and this is equal to 3A dash by 2. So here the separation is 3A dash by 2. For the first line transition, that is the D2 line, that is the transition from 2p 3 by 2 to 2s 1 by 2, the wave number is 16973.4 centimeter inverse. And for the second line transition, that is the D1 line, that is a transition from 2p 1 by 2 to 2s 1 by 2, here the wave number is 16956.2 centimeter inverse. Here the separation is 16973.4 minus 16956.2, and this is equal to 17.2 centimeter inverse. Equating 1 and 2, we get 3 by 2 A dash is equal to 17.2 centimeter inverse. Therefore A dash is equal to 2 by 3 into 17.2, and this is equal to 11.4 centimeter inverse. So here the answer is option B. The next question is the spectral terms for a certain electronic configuration are given by 3D, 1D, 3P, 1P, 5S, 3S. The term with the lowest energy is, so here the spectral term that have the largest multiplicity should have the lowest energy. So here it is 5. 5 is the largest multiplicity. So the answer is option A, because here 5 has the highest multiplicity, that means it has the lowest energy. If the terms have the same multiplicity, the one with the highest orbital angular momentum, that means the highest L value, should have the lowest energy. Then for a subshell that is less than half filled, then the term with the lowest J has the lowest energy. Next question is the degeneracy of the spectral term 3F is dash. Here in the 3F term, 3 means it is the multiplicity, that means 2s plus 1 is equal to 3. Therefore, s is equal to 1 and L equal to 3 here. Therefore, J is equal to L plus S to L minus S, that is equal to 3 plus 1 to 3 minus 1, and this is equal to 4, 3 and 2. Then the total number of mj is equal to summation over j equal to 2 to 4 2j plus 1, and this is equal to 2 into 4 plus 1 plus 2 into 3 plus 1 plus 2 into 2 plus 1, and this is equal to 9 plus 7 plus 5, this is equal to 21. So here the degeneracy is equal to 21. So the answer is option D. The next question is for the case J is equal to L plus half, where J is the total angular momentum, the expectation value of S dot J in the nuclear ground state is equal to dash. We know that J is equal to L plus S, therefore J square is equal to L plus S the whole square, that is equal to L square plus S square plus 2 L dot S. Therefore L dot S is equal to half into J square minus L square minus S square. Therefore, L dot S is equal to half into J square minus L square minus S square, and this is equal to H cut square by 2 into J plus 1 minus L into L plus 1 minus S into S plus 1. This is equation number 1. And here it is given that J is equal to L plus half. Therefore, J into J plus 1 minus L into L plus 1 minus S into S plus 1 is equal to L plus half into L plus 3 by 2 minus L into L plus 1 minus half into half plus 1. Therefore, this is equal to L square plus 2L plus 3 by 4 minus L square plus L minus 3 by 4. This is equal to L square plus 2L plus 3 by 4 minus L square minus L minus 3 by 4. This is equal to L. Therefore, equation 1 implies L dot S is equal to H cut square L by 2. Therefore, S dot J, that is equal to S into L plus S, that is equal to L dot S plus S square. Therefore, the average value of S dot J, that is equal to the average value of L dot S plus the average value of S square. So, this is equal to H cut square L by 2 plus H cut square S into S plus 1, that is equal to H cut square L by 2 plus H cut square into half plus 1, that is equal to H cut square L by 2 plus H cut square into 3 by 4, and this is equal to H cut square by 4 into 2L plus 3. This is equation number 2. Here J is equal to L plus half, that is L is equal to J minus half. So equation 2 implies S dot J is equal to H cut square by 4 into 2 into J minus half plus 3, and this is equal to H cut square by 4 into 2J minus 1 plus 3, and this is equal to H cut square by 2 into J plus 1. But here in the options H cut square term is not given. So the most appropriate answer is J plus 1 by 2. Next question is for the O70 nucleus, the effective magnetic moment is given by mu effective is equal to EH by 2mc Gj, where G is equal to dash. So here for 8O70, the number of neutrons is equal to 9. So here it is the odd number. So the sequence of energy level can be right in the form 1s 1 by 2 2, 1p 3 by 2 4, 1p 1 by 2 2, 1d 5 by 2 1. So here the unpaired electron is present in 1d 5 by 2. So here J is equal to 5 by 2. So the magnetic moment is equal to minus 1.91 mu n. So In the case of oxygen, that means in 8 or 70, the number of neutrons is equal to 9. So the sequence of energy levels can be written in the form 1 as 1 by 2, 2, 1p 3 by 2, 4, 1p 1 by 2, 2, 1d 5 by 2, 1. So here the unpaired electron is present in 1d 5 by 2. So here J is equal to 5 by 2. Here it is the unpaired neutron. For unpaired neutron, and for J is equal to L plus half, here J is equal to L plus half because J is equal to 5 by 2 here. So for the J equal to L plus half and for the unpaired neutron, the magnetic moment is equal to minus 1.91 mu n. The general equation for the magnetic moment is G mu n J. Here J is equal to 5 by 2. Equating these two, we can write G mu n into 5 by 2. This is equal to minus 1.91 mu n. Therefore, G is equal to minus 2 into 1.91 divided by 5. This is equal to minus 3.82 divided by 5, and this is equal to minus 0.77. So the answer is option B. So here we need to understand some equations for the calculation of magnetic moment. For the unpaired proton, if J is in the form of L plus half, then mu z of P is equal to, that means mu z of proton is equal to J plus 2.29275 mu n. If J is in the form of L minus half, then mu z is equal to J divided by J plus 1 into J minus 1.29275 mu n. Then for the unpaired neutron, if J is in the form of L plus half, then mu z is equal to minus 1.9135 mu n, and if J is in the form of L minus half, then mu z is equal to 1.9135 J divided by J plus 1 into mu n. And here the total moment mu z is equal to mu z of proton plus mu z of neutron. Using these equations, we can calculate any question related to the magnetic moment. The next question is the term symbol for the electronic ground state of the oxygen atom is dash. For oxygen, the configuration is 1s2, 2s2, 2p4. So there are 4 electrons present in 2p. Here 2 electrons are paired and 2 electrons are unpaired. So L is equal to summation over ML is equal to 0 plus 1 is equal to 1, and S is equal to half plus half, that is equal to 1. J is equal to L minus S to L plus S, and that is equal to 0, 1 and 2. So since 2p shell greater than the half filled, so the J value corresponds to the ground state will be J max. That means J is equal to L plus S. So here J is equal to J max, that is equal to 2. So here the term symbol can be written as, the general term symbol can be written in the form 2s plus 1 Lj. So here this is equal to 3p2 because here 2s plus 1 is equal to 2 into 1 plus 1. So this is equal to 3. So the spectral term is 3p2. So the answer is option D. The next question is, an excited state of Ca atom is Mg 3p5 4s2 3d1. The spectroscopic term corresponding to the total orbital angular momentum are. The electronic configuration of calcium is Mg 3p5 4s2 3d1. For 3p5, L is equal to summation over Ml is equal to 1. And there is only one unpaired electron present here, so S1 is equal to half. And for 3d1, only one unpaired electron is present. Therefore here for 3d, as it is d, L is equal to 2, and there is only one unpaired electron, so S2 is equal to half. L is equal to L1 plus L2 up to L1 minus L2, that is equal to 1 plus 2 etc. up to 1 minus 2. So this is equal to 1, 2 and 3. For L equal to 1, the spectroscopic term is P. For L equal to 2, the spectroscopic term is D. For L equal to 3, the spectroscopic term is F. So this is the answer. This is the end of this video. Thanks for watching this channel.